right, we're going to look at problem 50 and draw some force vectors. So it says here's a stone sliding down a friction-free incline. So you have a stone rolling down a slope. Part A says identify the forces that act on it and draw appropriate force vectors. So we have kind of a couple forces at play here. One is the weight of the stone, and that's always acting straight down like this. So I'll just call that W, weight of the stone. The other force at work here is the support force, or the normal force that's going to go up like that. And there's also some friction happening here, but we're gonna ignore that for now. I'm just gonna call this N for normal force. So those two forces are happening. Now we're gonna use, in part B, we're gonna use the parallelogram rule to construct the resultant force. Remember from chapter 2, the resultant force is how are these two force vectors acting cumulatively, acting together with each other. And the way we do that is use the parallelogram rule. So I'm going to start by sliding the W vector up to the tip of the N vector, and I'm going to draw it the same length, draw it down like that, and then I'm going to slide this N vector, and I'm going to keep it parallel to itself, so we create a parallelogram, and I'm going to draw it just like that. And then when we want to see what the resultant is, I'll switch colors here, the resultant is going to be how these two are acting together. And if we draw it end to end, we see that here, the green arrow here, is going to be the resultant force. And so we can see the stone is rolling down the hill and it's gaining some speed because there's a force acting on it parallel to the slope. All right, so next problem, guys, is we're going to look at problem 54 in your book. If a woman weighed 500 newtons on Earth, remember newtons being a measure of weight, you can measure weight in newtons or pounds, but we're including the force due to gravity when we talk about weight versus mass. What would she weigh on Jupiter, where the acceleration of gravity is 26 meters per second squared? So we see that that because Jupiter is much bigger than Earth, it has a stronger pull due to gravity. So the first thing we want to do is we want to find the mass of the woman, because what we learned in our chapter is that no matter where this woman is in the known universe, her mass is an unchanging thing. It's a constant. What changes, though, is her weight, depending on how much gravity is pulling on her. So we know that on Earth, she's being pulled with 500 newtons of weight. We also know that on Earth there are 10 newtons in 1 kilogram. Okay, so taking this ratio, we get the mass of the woman is equal to 50 kilograms. You see the newtons up here cancel out, newtons divided by newtons, and then we get 1 over kilograms, and so the kilograms end up moving to the top, and we get 50 kilograms. All right, so then what we want to find is the weight of the woman on Mars. And the way we find the weight on Mars, weight is always the mass, which is that constant value we just figured out, times the acceleration due to gravity, which in this case on Jupiter is 26 meters per second squared. And a kilogram meter per second squared is the same thing as a newton. So when we take 50 times 26, we get 1,300 newtons. So therefore, this woman weighs 1,300 newtons. So we see she weighed 500 newtons on Earth. She weighs over twice as much, over 2.5 times as much on Jupiter, because Jupiter, due to it being so much bigger than Earth, has a much stronger pull of gravity, so she's going to weigh more.